Now, I'm going to make a plug. I'm going to make an advertisement for the linear model. So we're done talking about the linear model. Okay, I'm going to say it one more time. Not that I haven't said it enough, but I want to end this lecture at least saying it one more time. Okay. So the linear model is the first thing you should try. Or at least when you approach a problem, you should say to yourself, I'm going to try to solve this problem with the linear model. Okay, it works in practice, because if you think about the features carefully, you will get a good in-sample error, and then the linear model takes care of the E out to E in link, and so you will get good out-of-sample error. And I'm even willing to challenge anybody out there. You think you need a sophisticated model? Come, bring your data to me, bring your problem to me, and odds are I will be able to get a pretty decent solution with the linear model. So if you cannot do it with the linear model, you haven't thought enough about the problem. Think more about the problem. Now, of course, we have the linear model, and we have even the ability to tolerate error with the linear model, the pocket algorithm. Okay? But we also have this additional power of the nonlinear transform. But be very careful when using the nonlinear transform. You have to pick your nonlinear transform before you look at the data. Okay? So you have to choose your nonlinear feature transform before you look at the data. Always, 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 always. If you want to be able to say something about E out. If the only thing that matters is E in, you can do whatever you want. But if you want to be able to say something about E out, you have to choose your nonlinear transform before you look at the data. Okay. Linear model, I'm plugging it. It's fundamental. Okay. And as I already just described, in its own right, it's fundamental for solving problems. But even if you decide to go for more complex models, they are the building blocks. The linear models are the building blocks of these other models. So use the linear model and realize that it's worth getting to know the linear model very well. Make it your friend, your best friend. Okay? Because when we study neural networks, when we study support vector machines, we'll be digging back to the vault of the linear model. And let me just mention that everything I said today about the nonlinear transform, okay, it doesn't rely on the fact that we're doing classification. So you can use it for regression and logistic regression. The mechanics is exactly the same. You transform your data, okay, and then you use the linear model for whatever problem you're trying to solve in that transformed space. Okay, so if it's logistic regression, you minimize the cross-entropy error using gradient descent. If it's regression, you just have the one-step pseudo-inverse algorithm. In all those cases, what comes out in your nonlinear feature space Z is the weights W tilde. And now you want to apply your weights W tilde to a new test point. You just transform that test point and apply W tilde in that space. Okay. So, very powerful linear model. Use it. Checking out.